Hello everyone, this is the fourth video on the SMO Senior mock paper and we'll be going through questions 16 to 20. As usual, you can find the link to the problems in the description below. Now, for the last 10 questions, you'll expect to see a more unusual mix of problems, so maybe trickier geometry, combinatorics and number theory questions, and also algebra problems that are perhaps a bit less familiar. So here the questions may feel a little bit more tricky. Let's get started with question 16, where we are given 4 equal lengths, which is already quite nice. All of these lengths are equal to 10. There's a 40 degrees here, and a rather strange looking condition to do with AB and AC. Now we can fill in a lot of angles because we have an equilateral triangle here, so these are all 60 degrees. These would be 70 because of the isosceles triangle. It's just that we can't really get BAE. BAE doesn't seem to have much to do with anything at this point in time. So we have to use that strange looking condition to do with AB and AC. Now it tells you AB squared plus AC squared plus square root 3 times AB times AC equals to 100. And this kind of smells like the cosine rule. Right? The cosine rule has a square, and something times the product. So let's write down what the cosine rule would tell us. It would tell us that AB squared plus AC squared minus 2AB times AC times cosine BAC is equal to BC squared. Now AB squared plus BC plus AC squared matches perfectly. BC squared is actually 100, it's 10 squared, so that also matches. So really, this information gives us the value of angle BAC. Right? We can compare it to the problem and say that cosine BAC equals to negative root 3 over 2. Right? That would make the two equations exactly the same, so it has to be the only possible value. And this is a special angle. It tells us that angle BAC, because cosine inverse root 3 over 2 is 30 degrees, but this is obtuse and hence negative, so BAC is 150 degrees. Now the question is, so what? Because there's no more information left, right? We have used up everything in the question. So it means that for this AB squared plus AC squared plus square root 3 AB times AC equals 100. Once we have extracted the angle, there is nothing more we can say. So it means that all the equal lengths, apart from what we have done so far, must give us something a little more informative. In fact, what we can do is something like this. We realize that since D is equidistant to BC and E, we can draw a circle centered at D, passing through those 3 points. I'm not going to draw the whole circle, it's not very needful. And this 150 degrees has a pretty nice property. Since we have all the 60 degrees, 150 degrees, these are your nice angles. I can use this circle and draw in this line over here, and say that this 60 degrees will be twice of this angle down here, so it must be 30 degrees. And then the 150 degrees comes in handy, because 150 and 30 degrees sum to 180 degrees. So since those two sum to 180 degrees, it tells us that ABEC is a cyclic quadrilateral. Remember that when we say that it is cyclic, it means that all the properties that normally come along with a cyclic quadrilateral are now in play, which is quite a lot. Specifically for the one that we want, we can say that angle BAE is equal to angle BCE. which is equal to 130 degrees. So spotting this cyclic quadrilaterals is one of the early difficult tasks in geometry, meaning that for the SMO Senior and for other more difficult Olympiads, when you see a geometry question that you're stuck on, there's a high likelihood that there might be a cyclic quadrilateral that you need to spot. And that cyclic quadrilateral will give you a whole host of additional length and angle equalities. You just need to realize it is that. So given a lot of specific angles, you're trying to almost forcefully make one of these relationships occur. Alright, question 17. You have the sum of sine squared of, well, a lot of these angles. And from there we are supposed to determine 100a, which is usually just to make the answer an integer. So how do we go about adding all of these up? So clearly, when you say when you see a, sine squared 12, 24, 36, 48, these are just multiples of 12. So that's not really the difficult part necessarily, right? You can tell what these angles are. It's just that there isn't a specific obvious thing to do. Now our identities don't really give much for sine squared. Of course, you could also switch it to cosine squared, but that isn't really an easier version of the question. So what we can do is to use the cosine double angle formula to take away the squares first, because this is the identity we want to use. Sine squared theta is 1 minus cos 2 theta over 2. So I can convert all of these now to cosines of twice the angle. So 7 of these all have a 1/2. And now your angles become cosine 24 degrees, cosine 48 degrees, and so on. The last one is cosine 168 degrees. So we are left to figure out how to add up this bunch of cosines. Now this is an idea that I like quite a lot, which is that you can make use of the symmetry around the unit circle. So you can realize that 24, 48, all the way to 168, this is pretty symmetric. They are just evenly spaced angles. So let's draw a circle. Not a very nice one, but it will do for our purposes. So something like this will happen. You have got 24 degrees, 48 degrees, 72 degrees, 96 degrees, 120, 144, 168. Okay, this is not very nice, but you get the idea. It's not rotation, so it's not symmetric about the y-axis, right? Which is why this looks a little bit off. But they are supposed to be evenly spaced, notwithstanding my rather uneven drawing here. Now I can actually flip these over to make another copy, and these will continue to be evenly spaced around the circle. And there's kind of one missing angle down here, which is the 0. That's not included if I flip it over. Now look at all of these here. If we add up all the cosines, then just by plain old symmetry, it should sum to 0. Now the analogy I like to use is that imagine you have different people pulling evenly spaced around the circle on an object in the center. Then clearly it's not going to move. And so if it's not going to move, that means that from a bit of physics, the x and y components of the forces balance out. So that means the sum of the sines and the sum of the cosines should be still 0. So with that in mind, you can say that this is pretty easy to calculate because cosine 0 is 1. So the top half and the bottom half have to be negative half. And so 7 over 2 plus 1/4 is 15 over 4, and 100A would be equal to 375. Okay, so to be very clear, what I'm trying to say on the image on the right is that apart from this 1, which doesn't have a pair, all those in the top half and all those in the bottom half, in terms of their cosines, have to sum to the same thing because each of them pairs up. But when you add all of it up, you should get 0, which means that apart from cosine 0, which is 1, the other two must each contribute negative half. There's a way to do this using a telescoping sum as well. I'll leave you to explore that, but it is a lot less enjoyable than noticing something like this. Question 18. Suppose that there are exactly n distinct rational numbers among sine, cosine, tangent, cosecant, secant, and cotangent of theta. Given that theta is not an integer multiple of pi over 2, determine the number of possible values of n. Okay, first things first, not an integer multiple of pi over 2 isn't very important. It just makes sure that we don't have to deal with undefined values of any of these, because we have a lot of reciprocal functions here, and so a lot of them will be undefined at say 90 degrees or 180 degrees when sine or cosine becomes 0. So that's really the only significance of that. Now also take note that they're not asking you how many rational numbers there are, they're asking you how many different possible numbers of rational numbers are there, because n is the number of rational numbers, and specifically number of distinct rational numbers. So we're not looking for simply the number of rational numbers because it's quite possible to make all of them rational. But how many of them end up being distinct? So let's try this out. Now, it's quite obvious, as I said, that you can make n equals to 6. So all of them rational. For example, you can just let sine theta be 3/5 and cosine be 4/5 in the usual 3-4-5 triangle ratios. Then all the rest of them are going to be just fractions of these, and in a 3-4-5 triangle, all of these are going to be just different ratios of sine, so they are definitely all going to be different. So this would give you 6. It's not too difficult also to imagine you can get 0. If you want to get 0, all you need to do is to, well, make sine and cosine something weird. For example, sine could be square root 0.3 and cosine be square root 0.7, because remember sine squared plus cosine squared must sum to 1, so this is why I construct an example like this. Now, the rest of them will be again fractions to do with these, and if you divide or you reciprocal them, obviously they will still be irrational but all different. So you get no rational numbers. Now, at this juncture, we kind of realize there is something interesting going on. Based on our experimentation, and I keep saying about reciprocals, we know that these are just going to be reciprocals of one another. And if they are reciprocals of one another, it means that when one of them is rational, the other one would also be rational. So most of the time we would expect them to come in twos. Right? When you get one rational number, the reciprocal is also rational. So most of it should be even. So we can try to make the even ones work out. If n equals to 2, then one of our special cases, like let's say theta equals to pi over 3, which is 60 degrees, would work because sine would be irrational, root 3 over 2, but cosine would be rational. And if cosine is rational, that means that its reciprocal would also be rational, but the others will not. Now, if you want to make it n equals to 4, however, that does not work because if let's say you have sine and cosine being rational, then tangent should be sine over cosine. So it would also be rational. And if let's say cosine and tangent are rational, then tangent times cosine is sine. So that would also be rational. So 4 does not work for that reason. Now, there is one final catch here before we say that there are 3 possibilities, which is about distinct. Now, we need to be careful to check whether is it possible to make some of these overlap. And if some of these overlap, they may not necessarily be distinct. Now, we know that sine and cosine are always going to be having magnitude less than 1. Since I can assume they're all in the first quadrant, I'm just going to say less than 1. And these two are more than 1. The tangent is the one that can run all over the place. Now, you cannot have something like sine equals to tangent because that would require cosine to be 1 or sine to be 0, and all of these are all at special cases of multiples of pi over 2. In fact, you can't also have sine and cosine both be equal to each other and rational. You can't have secant and cosecant being equal because that's the same as sine and cosine being equal. So the only thing that can happen is that tangent and cotangent is equal to each other, which is when theta is 45 degrees. Now, if theta is 45 degrees, which is basically pi over 4, then sine and cosine will be 1 over root 2. Secant and cosecant will be square root 2. But tangent and cotangent will be equal to 1. So you get n equals to 1 because the tangent and cotangent are both rational, but the same rational number. And if they're the same rational number, then most certainly that doesn't count as more than 1, that counts just as n equals to 1. To get something like n equals to 3 or 5 is clearly impossible. You can't get 5 because if one of them is not a rational number, its reciprocal will also not. And to get n equals to 3, you would need a repetition as well as one pair. And it is pretty easy to see that that also cannot happen. So n equals to 0, 1, 2 or 6 are the only possibilities. And so there are 4 ways that this can happen. Now, for those of you who are a little bit more experienced with Olympiads, you know that what I've just given is not a complete proof, right? It's just a lot of intuition and rough explanations. So I'll leave that as a challenge to you if you want to try to write out a more systematic proof of this statement that you cannot have 3 different rational numbers or 5 different rational numbers or 4 different rational numbers. I'll leave that to you. It's not very difficult, but it's a little bit more technical than I would like to go into in the time of this video. Okay. Question 19. Let a0, a1, a2 be a sequence of real numbers defined as follows. a0 equals to 2, and then an plus 1 equals to half log base 2 of 4 to the an plus 11 for all n greater than or equals to 0. What's the smallest positive integer k such that ak is also an integer? Effectively asking you, when's the next integer going to happen after the first term a0? Well, we can start by possibly writing down some values. a0 equals to 2. Just using the definition here, a1 equals to half log base 2 of 27. Then A2, oh bother, this is a bit annoying already, right? We need to figure out how to calculate 4 to the power of this as nicely as possible. But here's where there is a simple but quite useful idea. You can use a change of base to make it into log base 4. You just say this is log 227 over log 2 of 4. So this is actually log base 4 of 27. Now once I see that, it makes the calculation a lot easier because this is no longer half log base 2. I can write it as log base 4 of 4 to the an plus 11. So the next one, for example, would just be log base 4 of 38. Then the next one, you just take 4 to the power of this plus 11 and log again. So that would be log base 4 of 49. And so on. You're just going to add 11 to the inside every time. In other words, your AK is log base 4 of 16 plus 11k. Because 2 is log base 4 of 16 is where we began from, and each successive term we add 11 to the value inside the logarithm. We are left to figure out when's this going to be an integer. Clearly not that soon, right? Because 16 plus 11k, powers of 4 are pretty far apart and it will not hit 64. The next one after that is 256, it will not hit that either. So how long do we need to go in order to find it? Well, that leads us to the real question within this. When will the inside be a power of 4? I'll write it as 4 to the n. When will it look like 4 to the power of n? And we can flip the question around. When will 4 to the power of n look like 11k plus 16? Now, 11k plus 16 is just any number which is 16 mod 11. And that is 5 mod 11. So when will it be 5 modulo 11 is the question. The answer to that question is that we can write down the pattern for powers of 4 mod 11. So you go 4, then 16, which is 5, we already knew that. 5 times 4 is 20, so that would be 9. 9 times 4 is 36, that would give me 3. 3 times 4 gives me 12, which is 1, and then back to 4 and 5 again. So the next one would be 4 to the power of 7. Which we would then need to calculate out. 4 to the power of 7, I shall give you the value, it is 16384. And those of you who know powers of 2, this is just 2 to the power of 14, so it may be familiar as a number you've seen before. Now finally, to get k, we just subtract 16 and divide by 11. Okay, and the answer is 1488. This is typical of a slightly more difficult question where there are two almost unrelated concepts being joined together. Right? One is logarithms, the other is modular arithmetic. And there are two things you don't really see next to each other most of the time. But really, the logarithms part of it is not the main challenge in the question. The main challenge in the question is recognizing how do you find 16 plus 11k to be a power of 4. The logarithm is just the setup work. So once you have gotten this, don't keep on trying to use logarithms. You can say that I finished the logarithms part of the problem and I should move on to treat this as a new problem. 16 plus 11k is a power of 4. When's the smallest time that this will happen? Okay. Last for this video is question 20. This is a pretty unusual coordinate geometry question because it mentions a cyclic quadrilateral. And you have coordinates A, B, C, D. I shall just draw a coordinate axis. So here A is 0, 3 root 3, so somewhere about 0, 5. You have got B equals to 9, 0. You've got C equals to 20, 22, pretty far away. And D is somewhere on the y-axis, 0, y. Roughly speaking, you can probably say it should be somewhere about here. Maybe because of the fact that angle ACB should be equal to angle ADB. So roughly it looks something like that. Okay, I'll just erase that stray mark over there. Now the question would be, how do I do this most efficiently? And honestly, when I set this question, I'm pretty open to any approach that you are comfortable doing. For example, you can try to make sure that the intersection of perpendicular bisectors is a single point. Right? That's the meaning of it has a circumcenter. You can try to use vectors, for those of you who are familiar, to do some angle equivalences. But the way that I intended to do this comes from the fact that for lengths in a cyclic quadrilateral, you can use a little bit of... Okay, I'll just draw it first before I say anything further. Okay, this is clearly not hitting that point, so I shall cheat a little and move it over. This is probably off the screen, right? Oh, it's still there, just nice. I'll call this point E. And what I want to say is that if this is a cyclic quadrilateral, then by my intersecting secants theorem, EA times ED should be equal to EB times EC. Now, why is it that I like this? Is because, well, I know point E. There is no unknown because AD is just simply on the y-axis, so this is also on the y-axis, and this is a pretty nice line. Right? Line BC, the gradient is 2, so this is actually y equals to 2x minus 18. So this point E would be just 0, negative 18. And since I know that point, there's really only one unknown. ED is the only unknown. Everything else is fine. Right, so I can just find all of the lengths. And EA would be 18 plus 3 root 3. ED is 18 plus y. EB is square root of 18 squared plus 9 squared, which is 9 times of square root 2 squared plus 1 squared is 9 square root 5. This is 20 squared, 40 squared, square rooted, so that's 20 square root 5. This portion here is just equal to 900, so 18 plus y is 900 over 18 plus 3 root 3. and you can subtract this off. Now technically this is already the correct answer mathematically, but the answer extraction requires that you get floor of 11y. Presumably one would gather you need to rationalize it in order to estimate it well enough. So if you did that, I will leave the details to you. Rationalizing the denominator as usual, just multiply by 18 minus 3 root 3. Simplify all of it. It cancels off surprisingly nicely. And 1 over 11 will show up, which is really the whole point of why I asked for floor of 11y. Okay, 402 minus 100 square root 3. So floor of 11y would be floor of 402 minus 100 root 3. So here, another reason is that I wanted you to be aware of the approximations of square root 3 and also square root 2 up to 2 or 3 decimal places. This is useful general knowledge for many of these Olympiad questions. So square root 2 is about 1.414. Square root 3 is about 1.732. You just need it to 2 decimal places here. So you would be subtracting about 173 point something. And so your answer would be 402 minus 174, which is equal to 228. Alright, so that's it for this video. It's a little bit longer because these few questions are a little more challenging. And I'll see you again for the last 5 problems in the final video for the SMO Senior. Thanks for watching. Hope you saw some new ideas in this video, and see you again for the last one.